So think about how much we're starting to see large language models, LLMs popping up everywhere in
Yeah.
systems that directly interact with the real world.
Yeah, things like AI assistants managing our schedules,
Yeah,
smart devices.
exactly. It's incredibly convenient, right?
Yeah.
But what happens when these powerful AI brains start processing information from sources that might not be trustworthy?
Mm-hmm. That's where things can get tricky.
Yeah, that's where a pretty sneaky security risk emerges, something called a prompt injection attack.
Right.
Imagine this. You ask your AI to email a document, maybe based on some notes from a meeting.
Okay.
But hidden in those notes is some malicious instruction, and it redirects that confidential file to someone else entirely.
Wow. Yeah, that's the core vulnerability we're going to unpack today.
Exactly.
And it's a vulnerability that, well, it just grows in significance as these AI systems handle more and more sensitive data. Which brings us, I think, to the heart of our deep dive today.
Which
A
is
really compelling research paper titled Defeating Prompt Injections by Design.
defeating prompt injections by design. I like the sound of that. So our mission today, for you listening, is to really understand what this paper is proposing. Yeah.
Exactly. We're going to get into a novel defense mechanism they call CaMeL.
CaMEL, like the animal.
Hey, well, it stands for Capabilities for Machine Learning.
Ah, okay. Capabilities for machine learning.
And what's particularly interesting, I think, is that CaMeL aims to safeguard these LLM agents from prompt injection attacks without needing to alter the underlying language models themselves.
Okay, that's a big claim. No changes to the LLM.
That's the idea. And our insights for this deep dive come directly from excerpts of the research paper itself, so we're getting it straight from the source.
Fantastic. So our goal then is to pull out the most crucial information, make this, potentially complex topic really clear,
Hmm.
and maybe even uncover some surprising aspects of this security challenge and how CaMEL plans to tackle it.
Sounds good.
Right, so let's jump in. The fundamental problem, these prompt injection vulnerabilities, what's the absolute core of the issue here?
Well, the central problem, as the paper really lays it out, it arises when these LLM agents interact with the external world.
Right.
And by extension, they encounter data from sources we just can't inherently trust.
Okay. Emails, documents, web pages.
Exactly. And this untrusted data can be deliberately crafted, designed to manipulate what the agent is supposed to do. Figure 1 in the paper gives a great illustration of this.
Let's walk through that.
Okay, so picture a user wanting to send a document to Bob, and Bob's contact details are supposedly in some shared meeting notes.
Seems straightforward enough.
But malicious text, maybe even invisible text, embedded within those notes. It could be designed to change the recipient or maybe even swap out the document being sent altogether.
Wow, that paints a really clear picture. It's not just about, altering the words that AI processes.
Yeah,
It's about changing the actual things the agent does in the real world.
precisely. The actions.
Now, the paper points out that current security measures, they often fall short. Why is that?
Well, a lot of current defenses, they rely on either training the models to be less susceptible,
Which is hard.
which is very hard, yeah, or they rely on using carefully constructed prompts, system prompts to guide the behavior and enforce security policies.
Right, setting the rules up front.
But the paper argues that these system prompts, they can themselves be vulnerable to manipulation. There's often just a lack of a really robust, formal way to consistently enforce security across all the diverse kinds of data these LLMs handle.
Okay, so the guardrails themselves can be bent. And what about this dual LLM pattern we've heard about? Using two different models, one for planning, one for execution. The paper suggests that's not a complete fix either.
That's correct, yeah.
Yeah.
While the dual LLM pattern separating the planning stage from the execution stage with two distinct LLMs, it does enhance security in some ways
How so?
by isolating the initial reasoning from potentially harmful content, basically. But it doesn't eliminate all the vulnerabilities. If we look at figure 1 again, even with a dual LLM setup, where one LLM plans the actions and another maybe extracts data from those meeting notes, the data flow can still be compromised.
Ah, okay, so the plan might be okay, but the data it uses...
Exactly. An attacker could still inject malicious content into the meeting notes, tricking that data-extracting LLM into pulling the wrong email address or the wrong file name, and that leads to the planned action sending the file being misdirected anyway.
So the overall plan, the sequence of steps, might be secure, but the actual information being plugged into those steps can still be tampered with. That makes sense. The paper even draws a parallel here to SQL injection attacks, doesn't it?
Precisely. Yeah, that's a great analogy to use. In a SQL injection, the attacker isn't necessarily changing the structure of the database query itself, right?
Right, they're messing with the inputs.
They're manipulating the input parameters, which can lead to unintended data retrieval or modification. And similarly, with LLM agents, even if an attacker can't fundamentally alter the agent's plan, manipulating these specific pieces of information, the arguments, the data that the agent uses, well, that can have serious security consequences.
Okay.
Figure 2 in the paper really highlights the core threat CaMeL is designed for. It shows a scenario where a confidential document gets diverted to an attacker because of a prompt injection hidden in a shared note, even though the user just wanted to share it normally.
Okay, so CaMeL is specifically designed to tackle these kinds of prompt injection attacks, the ones originating from untrusted data, emails, documents, whatever, that can ultimately change how the AI agent behaves and what it does with data.
That's the focus.
But it's also important to understand what CaMeL isn't trying to solve, right? What are its limitations? What kind of attacks is it not defending against?
Yeah, that's a good point. The paper's quite clear. CaMeL doesn't aim to defend against attacks that don't impact either the control flow, the sequence of actions, or the data flow of the actual information being used.
So, like, if the AI just gives a wrong summary.
Exactly.
Yeah.
Text attacks where the output might be misleading, but it doesn't lead to unwanted actions, like data being sent to the wrong place.
Yeah.
CaMeL isn't directly addressing that. If a prompt injection causes an AI to summarize an email inaccurately but doesn't trigger any further actions, that's outside its scope.
Okay. And phishing.
Similarly, it doesn't directly target prompt injection-induced phishing attacks. However, there is an interesting side benefit mentioned.
Sure.
CaMeL's system tracks the origin of data. It builds this data flow graph. And this information could potentially be shown to the user, helping them maybe spot suspicious content that came from an untrusted source.
So even if it doesn't block it, it could help flag it. That's useful.
Potentially, yeah.
Got it. So CaMeL has this very specific focus, protecting the agent's actions and data handling from manipulation via untrusted data. Now, how does it actually do this? The name, Capabilities for Machine Learning, suggests something about permissions or abilities.
That's a great observation.
Yeah.
CaMeL is presented as this novel defense, and it's inspired by fundamental principles from traditional software security.
Okay, borrowing from established ideas.
Exactly.
Right.
And crucially, as we said, it doesn't require any changes to the underlying LLM itself. Its core idea is to explicitly identify and control the flow of both actions, that's control flow, and information, that's data flow, that originate from the trusted user query, and then enforce clear security policies on how that information can be used.
Inspired by software security. That's a really interesting angle. What specific ideas from that field are we talking about here?
Well, the paper draws direct parallels to really well-established software security concepts. Things like control flow integrity.
Making sure the program runs in the expected order.
Exactly. And access control, who can access what resources. And information flow control, governing how data moves through a system to prevent leaks of sensitive information.
Okay, so instead of trying to make the LLM itself immune to these tricks, which seems really hard, CaMeL builds a secure structure around it. And these capabilities, it's not just a general term for what the LLM can do, is it? It's more specific.
Precisely. Yeah, in the context of CaMeL, capability has a very specific security meaning. Think of it like a digital permission slip that gets attached to every piece of data within the system.
Okay, a permission slip for data.
Yeah. These capabilities define and restrict how that data can be used. They control both where the data can go, the data flows, and how the data can influence the agent's actions, control flows. And it's all based on very specific security rules or policies.
Okay, so every bit of data has these attached permission slips dictating what can be done with it. How does CaMeL actually enforce these restrictions in practice?
Well, CaMeL essentially creates a controlled environment, kind of like a sandbox, where the agent's logic gets executed.
Okay.
It uses a custom Python interpreter. This interpreter is key.
Why custom?
Because it's specifically designed to keep track of where data comes from, its provenance, and to enforce those predefined security policies as the agent is running, step by step. By operating within this custom interpreter, CaMeL can offer security guarantees about data and control flows without needing to modify the LM itself.
A custom Python interpreter. That sounds like a pretty significant piece of the architecture. Let's dive into the main parts of CaMeL. The paper mentions 3 key components, right? Shown in figure 3.
Yes. The 3 main components are the Quarantined LLM, or Q-LLM, the Privileged LLM, or P-LLM, and the tools.
Okay, Q-LLM first. Quarantined, what does that do?
The Q-LLM's specific job is to take unstructured data from those potentially untrusted sources, like the meeting notes example we talked about,
Right.
and parse it into a structured format, something the system can understand and manage securely.
So it handles the potentially risky input. And the privileged LLM, the P-LLM, what's its role?
The P-LLM is responsible for generating the actual code. The Python code that expresses the user's request and figures out how to use the available tools to get the job done.
Okay.
It's given a system prompt. There are details in Appendix H.1 of the paper which explains the kind of code it should produce and what tools it has available.
Gotcha.
Then, based on the user's prompt, the P-LLM spits out a block of Python code, usually formatted in Markdown.
And these tools are the ways the agent actually does things in the world, yeah? Like sending an email or accessing a file.
Exactly. Tools are basically pre-built functions. They have specific instructions, specific APIs that the P-LLM can call upon in its generated code to perform actions. Like a send-a-mail tool that needs the recipient's address, the subject, the body, etc.
Okay.
The P-LLM's code will use these tools as needed to carry out what the user asks for.
So the P-LLM figures out the plan as code using these tools, and the Q-LLM helps it understand potentially risky data it might need. How does this code actually get run, and how are those security rules, those capabilities, enforced?
Right, this is where that custom Python interpreter comes back in. The interpreter takes the Python code generated by the P-LLM and uses Python's built-in ASYS library, that's abstract syntax tree, to break the code down into its fundamental structure.
Okay, analyzes the code structure.
Yep. And then it executes each part of this structure step by step, recursively. And importantly, as we mentioned, only a limited subset of Python is actually supported. This further reduces potential security risks. Again, the details are in Appendix H.1.
Makes sense. Limit the attack surface. And what happens if the P-LLM makes a mistake? LLMs aren't perfect programmers, after all.
Good question. The interpreter has a built-in mechanism to handle errors. If something goes wrong during execution, the interpreter will actually try to get the P-LLM to fix the code.
Oh, interesting. It asks the LLM to debug itself.
Kind of, yeah. Up to 10 times. It provides info about where the error happened and the type of error, much like a standard Python interpreter. However, and this is critical for security, if the content of the error message itself depends on untrusted data.
Ah, like data parsed by the Q-LLM.
Exactly. That part of the message is removed, it's redacted, before being shown back to the P-LLM.
Smart. So you don't accidentally inject malicious stuff through the error message?
Precisely. It prevents that potential feedback loop. The interpreter also remembers its state between these attempts, so variables and objects persist. One limitation, though. The current version of CaMeL doesn't have atomicity or rollback.
Meaning?
Meaning, if an operation with side effects like sending an email succeeds, but then a later part of the code fails, there's no automatic way to undo that first action.
Okay, that's a potential issue. But it tries to fix mistakes while being careful about not revealing potentially harmful, untrusted data back to the LLM. That's clever. The paper also mentions tracking beta dependencies where data comes from. How does CaMeL keep tabs on that?
Yeah, CaMeL maintains a graph. You can see it illustrated in Figure 5. It essentially maps out how different pieces of data are connected and where they originated.
Like a family tree for data?
Sort of, yeah. For instance, if a variable gets its value by asking the Q-LLM to process some untrusted input, the system records this link, this dependency.
And why is that graph so important?
It's crucial for enforcing the security policies because it allows CaMeL to see if a potentially tainted piece of data, something that came from an untrusted source, is being used in a sensitive operation.
Ah, okay. It follows the data trail.
Right. In the current setup, they mention that complex things like recursive functions aren't really a concern for this tracking yet.
Okay. And finally, the security policies themselves. How are they actually enforced using this dependency tracking?
So before the interpreter actually executes a tool with specific inputs.
Like before it actually sends the email.
Exactly. Before it commits to that action, it checks the relevant security policies. And these policies apply not just to the immediate inputs to the tool, but also to all the data those inputs depend on, going back through that dependency graph.
It checks the whole history.
Essentially, yes.
Yeah.
If the system detects a policy violation, for example, trying to use private data, maybe your bank balance, with a tool that has external effects, like sending it in an email to an untrusted address.
Yeah, that'd be bad.
Right. The tool's execution is stopped, blocked. The paper suggests that in a real-world app, instead of just stopping, These violations would probably trigger a prompt asking the user for explicit confirmation.
Okay, are you sure you want to send your bank balance to this random address? That makes sense. Trying to balance the security with making the system still usable.
Exactly. It's always a trade-off.
Now, the big question. How well does all of this actually work in practice? The paper describes an evaluation using something called Agent Dojo.
Yes. Agent Dojo. It's a benchmark platform actually presented at NeurIPS 2024, so quite recent. It's specifically designed to test how well these agentic AI systems perform tasks and, crucially, how secure they are in realistic scenarios.
What kind of scenarios?
It covers a range of different domains, things like managing a workspace, emails, calendars, files, banking tasks, travel planning, even using Slack. Each area has its own set of tasks and, importantly, its own potential attack vectors for prompt injection.
Okay, so a realistic testbed. How did CaMeL do? First, in terms of just getting the job done, its utility, its usefulness.
Well, Figure 6 in the paper summarizes the utility results, and the findings are generally pretty positive.
Oh, good.
Yeah. Across different LLMs, they tested models like Gemini and Claude CaMeL, didn't significantly reduce the agent's ability to successfully complete tasks compared to just using the model's own native tool calling APIs.
That's great news. So adding this security layer doesn't cripple the agent's ability to actually function.
For the most part, that seems to be correct. The paper does highlight one exception, the travel suite of tasks.
Ah,
What happened there?
CaMeL's performance was a bit lower there, and it seemed to be mainly because the APIs, the tools available for travel planning, had sort of unclear or poorly documented instructions.
making it harder for the P-LLM to generate the right code.
Exactly. It struggled to use them effectively. However, they noted that more advanced models, like one called O1, performed better even with those tricky APIs. So it suggests that as LLMs improve, or maybe just if tool documentation gets better, this issue can be lessened.
Okay, so a specific issue, but potentially solvable.
Right, and Table 1 gives more detail on other reasons Claude 3.5 Sonnet sometimes failed. Things like not enough context for Q-LLM, where the P-LLM didn't provide enough information for the Q-LLM to actually extract the needed data.
And the Q-LLM can't ask for clarification, right? Because that might open another attack vector.
Exactly, that's a current limitation. The Q-LLM can't communicate back what data it's missing without potentially creating a new way for attackers to inject stuff. So, while generally good on utility, there are still these areas for improvement.
Okay, so utility is mostly maintained, with some caveats. But what about the main goal? How effective is CaMeL at actually stopping prompt injection attacks, the security evaluation?
Right, this is where CaMeL really shines, according to the paper. Figure 7 shows some pretty significant improvements in security, and this is even without setting up specific granular security policies.
Just by using the CaMeL architecture itself.
Exactly. Just by separating the control flow, what actions the agent takes from the data flow, the information it uses CaMeL dramatically reduced the number of successful attacks in the Agent Dojo tests. This was across all the language models they evaluated.
Wow. Any specific numbers?
Well, for instance, with models like GPT-4o, the number of successful attacks went from, a noticeable number down to 0 when CaMeL's implemented.
0. That's impressive.
It is. And the paper also clarifies that the very few instances where attacks were still rated as successful against CaMeL, they weren't actually due to traditional prompt injection succeeding. They were edge cases or different kinds of issues.
Okay, that's a very compelling result. It sounds like just the design of CaMeL provides a really strong baseline level of security. What happens when you start adding those explicit security policies on top of that basic structure?
Yeah, Figure 8 looks into that. It illustrates how often these explicit security policies were actually triggered during both normal use and when the system was under attack.
And what do they find?
Interestingly, policies were triggered less often in the workspace tasks.
Why would that be?
They suggest it's likely because the information involved in those tasks, like email recipients or file names, can be more easily labeled or annotated. This allows for more precise, fine-grained policies that are less likely to block legitimate actions.
Easier to define clear rules.
Right. On the other hand, tasks in areas like Slack and banking saw more frequent policy triggers. This could be due to things like less clear ways to specify user accounts or data coming from potentially untrusted websites scraped by the agent.
More ambiguity.
Exactly. Or simply because the policies themselves were stricter by default, like the one governing the send money tool. Understandably.
Makes sense. You'd want tight controls on sending money. And how does CaMeL stack up against other defense methods people are trying? The paper mentions some comparisons within Agent Dojo.
Yes, Figure 9 presents a direct comparison with other security techniques that were also implemented and tested in Agent Dojo. Things like filtering, which tools the LM can use, a technique called spotlighting, which tries to highlight risky parts of prompts, and the prompt sandwich technique.
Okay, various heuristic approaches.
Right. They tested these using Claude 3.5 Sonnet, and the results clearly show CaMeL significantly outperforming these other methods in security.
How significantly?
CaMeL achieved 0 successful attacks in that comparison set. The next best defense, which was tool filtering, still allowed 8 attacks through.
0 versus 8. That's a big difference.
It really is. And it's also worth noting, they mentioned that even GPT-4o Mini's own built-in defense mechanism, which relies on like an instruction hierarchy, even that failed against some attacks in their tests.
But GPT-4 Mini with CaMeL.
GPT-4 Mini running with CaMeL showed no vulnerabilities in these specific tests.
Okay, so CaMeL seems to offer a demonstrably stronger level of security compared to these other existing techniques. The paper also includes some really interesting examples of more sophisticated, maybe more subtle attacks. What do we learn from those case studies?
Yeah, one particularly insightful example, detailed in Figure 10, shows how an attacker can cleverly manipulate the agent by turning data flow into control flow.
Data flow into control flow, how does that work?
Well, the attacker instructs the agent to, say, monitor incoming emails for specific instructions and then act on those instructions found within the email content. So the attacker is essentially using the data within the email to dictate the agent's behavior, the control flow. This could potentially lead to the execution of arbitrary code, depending on what actions the agent is allowed to take based on email content.
That's a much more subtle attack. It's not just injecting a direct command. It's manipulating the information the agent processes so that the agent indirectly carries out the attacker's will. Very sneaky.
It is. It highlights the complexity here.
The paper also discusses side-channel attacks. What kind of vulnerabilities do those represent? They sound even more indirect.
They are. Side-channel attacks, illustrated in Figures 12 and 13, exploit these indirect ways to glean private information. They don't necessarily break the rules directly.
Give me an example.
Okay, one example involves an attacker getting the agent to perform an action, like fetching an external image from a URL, but only if a certain secret piece of information is true.
Right.
By simply observing whether their server gets a request for that image or not, the attacker can infer the value of that secret bit of information. Did the condition trigger the fetch? Yes or no?
Ah, okay. Leaking info just by observing behavior?
Exactly. Another vulnerability they discuss involves how the system handles errors, particularly errors triggered based on the output of the Q-LLM.
How so?
An attacker could craft an input that causes the Q-LLM to produce a specific output if some private data has a certain value. This output might then cause an error later in the P-LLM's code execution.
Okay.
By observing whether subsequent normally visible actions are taken or skipped because the error stopped execution, the attacker can potentially learn one bit of information about that private data. Appendix A gives a really detailed example of this.
I remember seeing that, about trying to figure out if a user is meeting with someone named Bob.
That's the one, yeah. By manipulating meeting minutes, client meeting-minutes.doca, to potentially cause an error depending on whether Bob's meeting is confirmed internally.
Wow. These side-channel attacks are pretty concerning because they don't directly break the intended security rules about data flow, right? They leak information through these more indirect means.
That's the challenge, yes.
The paper mentions a strict mode in CaMeL. How does that help mitigate these kinds of threats?
Right. Strict mode. It's described in section 4.4. It's basically a way to strengthen the security posture by adding a stricter dependency rule.
What rule?
It requires that any statement executed after the Q-LLM is called must have a dependency on the arguments passed to that Q-LLM call.
Okay, what does that mean in practice?
It means that if a tool that has external effects, like sending data out, is called later in the code, and its inputs rely directly or indirectly on information that came from the Q-LLM processing potentially non-public data, that action will be blocked by default.
Unless
the user explicitly confirms it. So it forces user confirmation for potentially leaky actions that depend on Q-LLM output.
Okay, so it helps against those Q-LLM-induced errors leaking information.
It seems effective against those specific Q-LLM-induced exception side channels, yes. However, the paper acknowledges that adversaries might still try to trigger exceptions by manipulating the data that the tools themselves use, trying to cause a tool to fail based on private info. But they suggest this is probably more difficult for an attacker to achieve reliably.
So it tightens things up, but maybe doesn't close every single tiny side channel, which leads us to limitations. While CaMeL seems like a significant step forward, the researchers are also realistic about, what it can't do yet and where things might go next. What are some of the main challenges and areas for future work?
Yeah, they're quite upfront about that. They state clearly that prompt injection is not a completely solved problem, even with CaMeL.
Okay.
One key challenge is the burden it potentially places on users or administrators to actually define and maintain all those security policies. Getting them right is crucial, but could be complex.
Right, writing good security policies is hard in any system.
Exactly. And there's also that delicate balance to strike between strong security and a good user experience.
You mentioned the confirmation prompts.
Right. How do you avoid constantly asking users for confirmation for every little thing? That could lead to confirmation fatigue, where users just click yes or allow without really thinking, which kind of undermines the whole security benefit.
Yeah, we've all seen that happen.
And the potential for those subtle side channel vulnerabilities, even if they're hard to exploit and maybe low bandwidth, that also remains a consideration.
So still work to be done.
Definitely. But the paper emphasizes that CaMeL represents a fundamentally different approach. It's focusing on building a secure architecture, secure scaffolding around the LLM.
Rather than just trying to make the LLM itself inherently more resistant.
Precisely. Instead of just tweaking the model or the prompts, they're changing the system design using principles from software security. And the researchers seem optimistic that adopting this kind of architectural paradigm, this design philosophy, can unlock significant future improvements, not just in security, but maybe even in the utility and capabilities of these AI systems down the line.
Okay, so to sort of wrap up our deep dive into this research on CaMeL, it really presents a promising and pretty innovative way to think about defending against prompt injection attacks. Instead of solely relying on making the language models themselves magically secure, which seems like a really tough ask,
Yeah.
it focuses on the design of the system that uses the LLM, drawing inspiration from these well-established principles of software security.
That's the core idea.
The key insight here, I think, is shifting the focus. From trying to fix the AI's understanding, maybe, to controlling how it actually interacts with the world and its data.
Exactly. By explicitly managing the flow of actions, the control flow and the flow of information, the data flow, and by enforcing security policies through that custom interpreter environment, CaMeL provides a long layer of defense. And the evaluation suggests it significantly reduces the risk of successful prompt injection attacks, especially those originating from untrusted data sources.
And for you listening in, you've now taken this deep dive with us into this fascinating research. You've hopefully gained a solid understanding of how CaMeL works, how it manages the what to do and the what to do it with, and how it uses those security rules, those capabilities to try and protect LLM agents.
Which, raises a really important question for all of us to ponder as we finish up. As these LLM agents become more and more integrated into our daily lives, our work, handling increasingly sensitive information, how will approaches like CaMeL shape the future of AI security?
Yeah.
How will we find that right balance between the incredible potential and power of these AI capabilities and the absolute essential need for robust safeguards? What other challenges do you, listening, foresee in making sure we deploy these advanced systems securely?
Some really thought-provoking questions to leave you with. Thank you so much for joining us for this deep dive into a truly fascinating and I think really important area of research. If you're keen to learn even more, we definitely encourage you to check out the original research paper. You can find the identifier in our show notes for all the intricate details. And keep thinking critically about the security of the AI systems that are rapidly becoming such a big part of our world.